Did you know when a charged particle moves through an electromagnetic field, it experiences a force?
It is called the Lorentz Force.
Which is the combination of magnetic and electric forces created by an electromagnetic field.
Hi, I'm Reggie.
Hi, I'm Bea.
Hi, I'm Luis, and together with us is Yul.
We will discuss and review the concept of Lorentz Force. First, let's determine what the Lorentz Force is and who invented it.
Having a hard time understanding the right-hand rule? Well then, we'll explain to you the simplest way.
After knowing those, then we'll proceed to solve example problems and getting the Lorentz Force.
Now, should we stop learning or continue absorbing knowledge? A charged particle in an electric field will always feel a force due to this field of magnitude.
And the charged particle in a magnetic field will only feel a force due to the magnetic field if it is moving with a component of its velocity perpendicular to the field. If it moves parallel to the magnetic field, it experiences no force.
These two forces are often studied separately, but the sum of these two forces creates a force that we call the Lorentz Force.
It is an electromagnetic force experienced by a charged particle both in an electric and magnetic field.
It was discovered by a Dutch physicist named Hendrik Lorentz, which is why the Lorentz force is named after him.
This force is critical to understanding the behavior of charged particles in a variety of physical situations, ranging from fundamental physics to technological applications.
We will show you an illustration of how Lorentz force exists.
Observe the setup. A battery is connected to a circuit with a wire shaped like a pendulum, and a permanent horseshoe magnet is placed around it. First, click the close switch button to close the knife switch and complete the circuit. The black arrows indicate the direction of the current flow. Second, watch as the pendulum swings toward the battery, which happens due to the interaction between the magnetic field in the wire and the magnetic field from the horseshoe magnet. 3. Click Show Wire Field Lines or Show Magnetic Field Lines to display how the magnetic field interact, generating the Lorentz force on the pendulum. 4. Try clicking the flip battery button. You will see how reversing the current direction changes the magnetic fields and pushes the pendulum in the opposite direction. 5. Finally, press the flip magnet button to observe how switching the poles of the magnet also influences the pendulum's movement. We observe that the direction of the pendulum varies depending on the direction of the flow of current and the pole of the magnet.
We can determine in which direction the electron is deflected through the right-hand rule. These four fingers point the direction of the magnetic field, whereas your thumb points the direction of the positive charge movement. Lastly, your palm points the direction of the force or the direction of where the Lorentz force is exerted.
To easily understand how the right-hand rule works, here are the examples. We have our velocity moving upwards, so we point our thumb up. The magnetic field is represented by a bunch of X's, which indicates the field is directed into the page. Here's how we apply the right-hand rule. First, point your thumb straight upwards because the particle is moving upwards. Next, point your fingers into the page, since the magnetic field is into the page, represented by the X's. Finally, your palm will face towards the left. Therefore, for a positive charge, the Lorentz force will be directed to the left.
Because our velocity is going to the left, so my thumb is going to the left. And then the magnetic field is pointing down, so I need to point my fingers down. So as my thumb is facing towards me or away from the paper, so that's the direction of the force.
In these examples, we have observed the direction of the Lorentz force is perpendicular to the direction of the moving charge and the magnetic field. We've now understood what the Lorentz force is and how the right-hand rule works. Next on the list, solving example problems.
The formula to be used is F equal to Q parenthesis E plus B XB, wherein F is the total force on the particle vector, Q is the charge of the particle, E is electric field vector, B is the velocity of the particle vector, B is the magnetic field vector, and X represents the cross product. The force consists of two components. The first one is electric force, which means QE, which acts in the direction of the electric field. The second one is magnetic force, which means Q parenthesis B times B parenthesis, which is perpendicular to both the velocity and the magnetic field. Would you like an example calculation? Problem 1. Force due to an electric field. Let's substitute the values. Force is equal to 1.6 times 10 to the negative 19 coulomb times 500 Newton per coulomb. Force is equal to 8.0 times 10 to the negative 16 Newton.
Using the determinant method for the cross product, we will now solve for the value of the I, J, and K components. To solve for the value of the I component, we will cross-multiply the values of J and K components. 0 times 0.2 minus 0 times 0. The answer is 0. To solve for the J component, we will cross-multiply the values of I and K components. 3 times 10 raised to 6 times 0.2 minus 0 times 0. The answer is 0.6 times 10 raised to 6j. Lastly, to solve for the K component, we will also cross-multiply the values of I and J components. 3 times 10 raised to 6 times 0 minus 0 times 0. The answer is 0k. So we have 0i minus 0.6 times 10 raised to 6j plus 0k. This is equal to negative 0.6 times 10 raised to 6j. And that is the value for the product of the magnetic field and the velocity. Finally, we can solve for the force due to a magnetic field. So F is equal to negative 1.6 times 10 raised to 19 times negative 0.6 times 10 raised to 6j. The answer is 9.6 times 10 raised to negative 14 Newton. The force on the electron is 9.6 times 10 raised to negative 14 Newton in the positive y direction. For our last sample problem, example number 3, combined electric and magnetic forces. Using the Lorentz Force formula that was presented a while ago, we will start by solving the value for the electric force. To get the electric force, we will multiply the value of the charge and the electric field. Substituting the values using the FOIL method, we now have the value of. To get the value for the J component, we will cross-multiply the I and K components. And lastly, to get the value for the K component, we will also cross-multiply the I and J components. Now multiply the value that we had solved to the charge. And lastly, the last step is to compute for the total force. We hope you learned a lot in our discussion today. Bye!